All right, mathletes, so let's go ahead and let's dive into this integration method using substitution, all right, also known as that U Substitution Method. So let's start off with let me walk down memory lane, because I feel, right, that many of you were where I was many years ago with the confusion, right? What's going on here? So let me set the scene here to kind of help you out, because a lot of people, they make the mistake and they just say like, show me examples. But once I show you why and how, then you don't need these thousands of examples, right? You're gonna have the understanding and you're gonna be able to work your way through any of these problems. So let's dive in here. All right, so let's start off with this. Remember that chain rule for derivatives, right? So the chain rule, we used it when we had a composition of functions, right? One function inside of another function. And what we did when we applied the chain rule is we took the derivative of that outside function, right? And then of course that inside function remained the same, it was still inside, but it was inside now of the derivative of that outside function. And what do we do? Well, then we multiplied it by the derivative of that inner function. All right, so what we had is we had this composition of functions that we are working with initially, right? So what we have is we have this corresponding integral rule, right? So we still have the same idea, but now we're working backwards. All right, so now when we're taking the antiderivative, right, of where we left off, right, what we're gonna get is we're gonna get again this composition of functions here. And this idea right here is the money maker. So what I want to do is I want to break up what is it that you're looking for and how do I work with it. All right, so follow me. All right, to help us set the scene, let's go ahead and let's take the derivative of sine of x cubed. All right, so again, we're taking the derivative and we have a composition of functions, right? We have our outer function and then you have your inner function right here. So according to our rules, right, we take the derivative of sine, we know is cosine, and our inner function is going to remain the same, but then we're going to multiply it times the derivative of that inner function. And so the derivative of x cubed is 3x squared. So what we have here, right, you have the derivative of the outer function. And what did we do? We left that inner function the same. And then we multiplied it by the derivative of that inner function, right? The derivative of whatever this inner function was, which we called g of x, right? So what we're gonna do is we're gonna use this idea and we're gonna work backwards in a sense, right? So again, what we're gonna do is we're gonna undo all this to help us understand this U substitution method and to help us understand what is it that we're looking for. All right, so let's dive in. All right, so now let's go backwards just like we said. So we're gonna take the antiderivative of cosine of x cubed times x squared dx. All right, so what are we looking for? Like, how do I know I could use the U substitution, or maybe that's the route I wanna go? All right, so the first thing I want to say is what's giving us like the green light to use the U substitution? Well, what we're looking for is we're looking for the following format, if you will. So you have some function, we'll call it f, right? And in this function, we're gonna have a composition of functions, right? And what we already talked about is we want this f to be the result. We want that to be the derivative of, so we want this cosine to be some derivative of some function that we're going to call f, right? And it's going to be composed with some function g of x. And what we want it to be multiplied by is the derivative of g of x, or some form of it. So again, we're going to do some manipulation to try to get it to look like g prime of x, right? So this is the form that we want to try to get it into using algebra and of course using our calculus, right? We want to get it in this form so that we could apply this U substitution method to it. All right, So as I'm looking at this, as I'm breaking it down, notice I have a function inside of a function, right? And it looks like if I take the derivative of this inner function, I can produce, right, using some algebra, x squared dx. All right, so it looks like I can use the U substitution method here. So how do you actually use the U substitution method? Well, here we go. So what we're gonna do is we're gonna let U equal, and this is the most important part, let U equal, in this case, I'm gonna let it equal the inner function, all right? And we have to, through practice, right, we have to get comfortable with this. So I'm gonna say let U equal x cubed. And when I take du, when I take the derivative of both sides, right, I'm gonna get 3x squared dx. All right, and remember, my goal is to get this derivative piece, right? Once I take the derivative of that inner function, I want it to get it to look like this, but there's a problem, there's no 3 here. Well, there's an easy solution, right? So all we're gonna do is divide 3 on both sides, right? Because once we do that, then we know that du over 3 equals x squared dx. And now what I'm gonna see is this x squared dx, right? That's exactly what we have right there. So when I go back and I do this substitution, right, what I'm gonna do is I'm gonna now let x squared dx, I'm gonna let that equal du over 3, and we already said that u is gonna equal x cubed. So wherever I see x cubed, I'm gonna replace it with the u. Why? Well, let's go ahead, let's do it, and let's see what happens, right? Well, let's see why. So let's take the antiderivative, let's do our substitution, and now we have cosine of u, right, times, and remember, we're making the substitution here. We're no longer gonna write x squared dx, now we're writing du over 3. So times du over 3. Notice we're dividing by a constant, so I could move the division by 3 right here, which would be the same thing, or I could move that 1/3, right, that's what it is, out to the front. So let's do that. So I'm gonna move this 1/3 out to the front, and so we have 1/3 times the antiderivative of cosine u du. Well, now when we try to take the antiderivative of this, right, of cosine u, we know what that is. It's much, much easier than trying to take the antiderivative of this over here. So just like we usually did with substitution methods, we use the substitution method to make the algebra much easier to work with, right? Or in this case, the trig. But we're trying to simplify this, or trying to rewrite it creatively so that we are able to reach our goal. And our goal here is to take the antiderivative of this, and now we're able to do it much more easily, right? Because now this is no problem to handle. This was a problem. So again, that's what the substitution method allows us to do. It allows us to take this hard antiderivative and make it much easier. So let's go ahead and let's take the antiderivative of cosine u. So we're left with 1/3 times sine of u. But again, recall that we didn't want the antiderivative. Everything was in terms of x, right? We didn't want it in terms of u. So the very last step is now we're going to do back substitution. We know that u equals x cubed. So wherever I see u, I'm going to replace it with that x cubed because we wanted everything in terms of x. So we're left with, oh, and some of you are screaming at me, plus c, right? So we have 1/3. We're not writing sine u anymore, sine of x cubed, right, plus c. So there's our big idea. So now we could jump in here and let's get some more practice with different types of problems. All right, so follow me. All right, so now that we got the bigger picture, let's go ahead and think about this. So notice I have this square root function, so I'll call that like my outer function, and I'm thinking this is gonna be my inner function. right? And when I take the derivative of this inner function, hopefully I could produce, using some algebra, right, manipulation, I could get this x. So let's go ahead and let's try some things, right? So again, don't just stare at it. That was one of my techniques when I was in my calculus class. You got to get your hands dirty, right? You got to make mistakes, and that's okay, right? That's part of the learning process. So let's let u equal the 1 minus x squared. All right, so let's use the substitution method. All right, and again, we're gonna take the derivative. So let's take the derivative of both sides. So we get du, that one's going away, and we're gonna get negative 2x, and of course, dx. All right, so write that down. First step, we're gonna make our substitution. And when you're doing that, all right, and you take your derivative, what you're taking a peek at, what you're looking at is, do I get this x dx, right? Does that come out of it? Well, there's my x dx. I don't need this negative 2, so let's move it to the other side. So I'm gonna go ahead and divide both sides by negative 2 because I don't need it, all right? It's not part of my original. So I get du divided by negative 2 equals x dx. And again, if you're confused by that, I need an x dx, right? So when I substitute, there it is, but nowhere in here did I have that negative 2, so that's why I got rid of it, okay? So when I substitute, right, I know that this x dx, right, my x dx is gonna be replaced with du divided by negative 2, all right? And then I know that 1 minus x squared, this whole thing is gonna get replaced with u. So now let's go ahead and let's replace all these pieces. So let's do the u sub. So after we do the u sub, we're now left with, let me pick a different color here, the antiderivative of the square root of u, and then we have du over negative 2. Again, that negative 2 is just a constant, excuse me, a negative 1/2, right? Because that negative 2 is in the bottom. So we have negative 1/2, it's a constant. So let's move it out to the front. So let's go ahead and do that. So this is really negative 1/2, right? We're bringing out to the front, and we're left with the antiderivative. What's another way of writing the square root of u? That's right, u to the 1/2 power. So again, all your algebra skills are always going to come back into play, and that's where students really struggle. Is there's a lot of gaps in their algebra. So take a look at some of my other videos to help you out with your algebra skills, right? Because again, it's such a huge part of calculus. And now this, the antiderivative of u to the 1/2, much easier than what we started with, right? Absolutely, much easier. All right, so now let's go ahead and take the antiderivative of this, which is much easier than taking the antiderivative of this here. All right, so what are we left with? We're left with negative 1/2. All right, and don't forget our power rule. So what we're going to be left with is we're going to multiply that times 2/3. All right, so you're going to multiply that 2/3. We know we're going to go ahead and add 1 to our exponent, so we're going to get 3/2 right there. And of course, don't forget to add our constant c. All right, so now everything we have here, we've taken the antiderivative. Well, last thing, right? Last thing is we don't want it in terms of u, we want it in terms of x, just like we started. So now we're just going to use that substitution. Wherever you see u, you know you're going to replace it with 1 minus x squared. So let's go ahead and do that. So you're left with negative 2/6, which reduces. So these 2's cancel. So we're going to be left with negative 1/3. The u we know is 1 minus x squared raised to the 3/2 power plus c. All right, and if you want, you could rewrite that as a radical, but we're gonna leave it just as is. All right, so I wanna look at a case that doesn't always follow that idea of a function inside of a function, because right now it's probably looking like we're always choosing that inner function, which is not always the case, right? A lot of times it is, but it's not always the case. For example, when we're looking at these trig problems here, right, like this one right here, if I were to let u equal 3x, then how am I going to get rid of, say, a tangent or a secant squared, right? It's not going to happen. So we have to be creative. And again, this is where knowing your trig identities is really going to help you out. And of course, your derivatives. So let's go ahead and let's dive in here. So here I'm going to let u equal, let's try tangent of 3x. And the reason I'm choosing tangent, and again, this is going to come with your experience and your knowledge of derivatives, is when we let u equal tangent, when I take the derivative of both sides, we could see that tangent squared of 3x is going to come out of there. And of course, times the derivative of the inside, which is 3 dx. All right. So what do you notice? Well, the derivative, right, shows up right here. And of course, we don't need that 3. So I'm going to go ahead and divide both sides by 3. But again, when you're making that substitution, when you take that derivative, whatever the result is, should take care of the remaining pieces of that substitution, right? So something to keep in the back of your mind. And what I would always do, especially if you're working with these trig identities and trig functions, is make sure you practice or review your derivatives of all these trig functions, all right? It's gonna save you a lot of time and headaches. So let's go ahead and let's divide both sides by 3. So divide both sides by 3 here. So you're left with du over 3 equals secant squared 3x dx. All right, and we see that. Let's do some highlighting. This right here, right, we could see when we do that substitution is right there. And we're going to substitute that with du over 3 because that's what it equals. All right, and then wherever we see tangent of 3x, we're going to replace that with u. So let's go ahead and let's do that substitution. All right, so let's go ahead and substitute everything in and let's see what we get. So now we have the antiderivative of, we have du over 3. And then on the bottom where we once had the tangent of 3x, we now know we just have the u. So let's go ahead and put that u down there. All right, we got to put a multiplication sign. So that 3, right, it's a constant. So let's move it out to the front just to make life a little easier. So we're left with 1/3 times the antiderivative of 1 over u times du. And what's great is we know the antiderivative of 1 over u, all right, which is much, much easier than all this over here. So really, really good news. So let's go ahead and take the antiderivative and you're left with 1/3 times ln, right, our natural log. Don't forget that u is, we're gonna have the absolute value there. So times the natural log of the absolute value of u, and then don't forget our plus c. And now that we've gotten to these great habits, we know that u is tangent of 3x. So we're left with 1/3 times ln of the absolute value tangent of, oh, sorry, all my little markers are getting in the way. Tangent of 3x. I didn't mean to change colors, but it's all good. And all that's inside the absolute value plus c there. All right, folks. So follow those easy 59 steps and you're done. All right, folks. So hopefully we're able to help you out get a better understanding of this U substitution method when you're integrating. So again, do us a favor. We work hard behind the scenes for you. So if you wouldn't mind hitting that like button, subscribing, telling a friend, or 10,000, and we'll see you mathletes in our next video. Peace.